All right, we're going to continue on in learning how to integrate more specific situations now that we have U substitution and we can use that. So we still need to know a little bit about integrating logs and exponential functions. We need to learn about integrating inverse trig functions, and we need to learn about integrating all sorts of other things when stuff starts to get more complicated. So the first thing we're going to look at is integrating log and exponential functions. And I want to address something that I referred to in our very first video about antiderivatives. And in that video, I gave you guys a shortcut. I said if the derivative was x to the n, then the antiderivative, or the original function, was x to the n plus 1 divided by n plus 1, but this only worked if n did not equal -1. And this is a rule that we've been using a lot. And I told you guys that I would address this situation in the future so you guys could see why it didn't work if n equaled -1. And so that's what I'm going to talk about first, and then I'll go into the shortcuts that we're going to be using. So if we tried this problem using n equals -1, then that would be me saying that f prime of x was 1 over x, which we could think of as x to the -1 power. And if I tried to use this rule on this problem, then I would say, let me add 1 to my exponent, and -1 plus 1 is 0, so then I would divide by 0. And so then I'd say, okay, my original function must have been x to the 0 divided by 0, which is just 1 over 0, which is undefined. And so that's why you can't do this problem. You can't use that shortcut if n equals -1. And if you think about it, when we were taking original functions, there was never a point where we could take the exponent, move it to the front, subtract 1 from it, and get the result of 1 over x. That never happened. It was actually a different function that gave us a derivative of 1 over x. And some of you guys might already know what it is, but the shortcut we're going to memorize for this, so we're going to think backwards now. If I got 1 over x as the derivative for something, the derivative that I was taking was of ln x. So now if I'm taking the antiderivative of 1 over x, I get ln x plus c. Now you'll notice that my x is in an absolute value symbol, and that's me recognizing that you can only ln things that are positive. And so what I'm doing is, as I'm writing this antiderivative, I'm keeping that in mind. I'm saying this only works for positive values of x. It doesn't work for every single x I can think of. The other shortcut we're going to look at is e to the x. And this one's pretty easy. We just say the antiderivative of e to the x is e to the x plus c. And that's because if you guys remember, when we took the derivative of e to the x, we always got e to the x. And then the antiderivative of a to the x dx is a to the x divided by ln a plus c. And these, again, you can refer to these notes for today if you want, or you can just start getting your yellow sheet out when we do integrals, because all these little shortcuts are on your yellow sheet, so you have them all in one place. All right, so we're going to go ahead and work through some example problems. And so the instructions for all of these are just going to ask you to integrate each of the problems. So the first problem we're going to do is x over x squared plus 1 dx. And what we're going to notice is we're getting to the point where every single problem we do is going to have U substitution, or like 95% of the time they're going to have U substitution. And so we're going to have to start to get better at recognizing what the inside of the function was and what the derivative of that inside of the function is. So here we can think that the inside is x squared plus 1, and the derivative of that is going to be part of the x. Or we can think that the inside function was the x, and the derivative of that is somehow the x squared plus 1 on the bottom. So usually you have a couple different ways you can think of it, and when you think of it that way, there's going to be one clear right answer. For example, if I used u as just being the x on the top, then the derivative of u is just 1. And that is not what the bottom is. So that would not be the way to go for this problem. The best way to go for this problem would be to say that the u is the x squared plus 1 on the bottom. And that's because when we take the derivative of u, we get 2x plus 0 dx. And while a 2x doesn't show up in the problem, an x does. And if I think about this as a fraction, because I know this is a problem that's a fraction, that would be 2x over 1. And so it would make sense that our derivative would be the x that's on top. So that's something to keep in mind as we're working with u substitution and trying to get better at it. So here I don't have a 2 hanging out in the problem. I don't have a coefficient of 2. So that means I need to divide this side by 2 and divide that side by 2. So du over 2 equals x dx. And now I'm ready to go ahead and write my problem in terms of u. So I'm integrating 1 over u, and then instead of, so that takes care of the x squared plus 1 on the bottom, and then instead of the x and the dx, I'm going to write du over 2. So now I can go ahead and take that 1/2 and pull it to the front. So I've got 1/2 times the integral of 1 over u du, and so the integral of 1 over u is ln u. Don't write the integral. So I've got 1/2 times ln of u plus c. And now I can go ahead and put the u value back in there. Now there's a lot of confusion sometimes over when you need the absolute value symbol, when you can get rid of the absolute value symbol, when you should leave the problem looking like this, when you should use your property of logs. So here I put the absolute value symbol in there just because that's my shortcut, and I'm going to say, yep, this is a good answer. But if you look at what's inside of our ln, x squared plus 1 is always going to be positive. Like there's no number for x you can plug in that would have made that negative. So this problem, if you didn't write it in an absolute value sign, you'd still be right because it would always be positive, and that would be within the domain of a log function. The other thing we want to consider is that this 1/2, if we use property of logarithms, and an ln is a logarithm, if we use properties of that, then that 1/2 is really an exponent to this stuff that's inside. And when you have an exponent of 1/2, you actually have a square root. So we could rewrite the same problem as ln of the square root of x squared plus 1 plus c. And again, square roots say I'm going to have the positive version of this, right? Because it doesn't say negative square root, it just says square root. So we don't really need those absolute value symbols there. So with this one problem, because of the subtleties of logarithms, there's a few different ways I could see the answer written, and that's one thing you'll have to keep in mind as you do these multiple choice problems. Okay, let's do problem 2. This one's going to be a definite integral, and we're going to evaluate from 1 to e of ln x divided by x dx. So again, I have to think about what the inside function is versus what could be the derivative of that inside function. So I could think of the inside function as ln x. I could think of the inside function as like a 1 divided by x. I could think of the inside function as just the x on the bottom. But however I think of it, I have to make sure that some sort of the derivative is present in the problem. And the more problems you do, the better you'll get at this. So for this particular problem, the u is ln x. And the reason that the u is ln x is because the derivative of u is 1 over x dx. And I can see in the problem that if I ignore that ln x, then the rest of the problem is 1 over x. So I can see that that derivative is present in the problem. So I'm going to go ahead and rewrite this problem. If the ln x is my u, then that gives me u. And then the 1 over x dx is just the du. All right, so there's my integral. Now I have to rewrite this integral with those ends, the upper bound and lower bound. So I'm going to say u of e equals ln of e, and u of 1 equals ln of 1. All right, so ln of e is 1. ln of 1 is 0, and that might be something like you could plug it into a calculator if this was calculator active, but if it wasn't, then you would need to have those memorized, and those are fairly common values of ln to show up. So it'd be good maybe if you don't have it already written down to write those down on a cheat sheet somewhere. So we are going to integrate u on the interval from 0 to 1. So now I can go ahead and do my antiderivative shortcuts. So I've got 1 plus 1 divided by 2. So this is going to give me 1/2 u to the second power evaluated from 0 to 1. And that's 1/2 times 1 squared minus 1/2 times 0 squared. So that's just 1/2 minus 0, which is 1/2. All right, for the third problem, we're going to do the integral of x squared e to the x to the third dx. So I have to think about what my inside function could be. I could say my inside function is x squared, but I don't see the derivative there. I could say my inside function is e to the x to the third, but there's no derivative of e to the x to the third. I'd have to see another e in the problem. I could say my inside function is x to the third, and that makes sense because if I take the derivative of x to the third, I can see that in the problem. So I'm going to say that u is x to the third, and then that means that du is 3x squared dx. So I see the x squared right there. I don't see the 3, so I'm going to go ahead and divide that over to the other side. So I've got the integral of e to the u, and then in replacement of the x squared and the dx, I have du over 3. So I'm going to go ahead and rewrite this as 1/3 times the integral of e to the u du. And when I take the antiderivative of e to the u, I just get e to the u. So that's 1/3 e to the u plus c. And then I can plug the u back in there. So that's 1/3 e to the x to the third plus c. And just a reminder that if you want to do check your answer for a problem like this, you just need to take your final answer and take the derivative of it, and then that would get you back to the original problem. Okay, we're going to do one more example, and I'll leave some for class tomorrow. So this one is going to be the integral from 0 to 1 of e to the negative 3x dx. And so my u value is going to be negative 3x. The derivative of u is negative 3 du. And I don't see a negative 3 in the problem, so I'm going to go ahead and divide that. Not du, dx. So I've got the integral, I'm not going to say from 0 to 1, I'm going to have to redo that, but that's going to be e to the u, and then instead of writing dx, I'm going to write du over negative 3. So I can rewrite this integral that I'm taking. It's going to be negative 1/3 e to the u du. And then I have to figure out what my interval is. So we're going to say u of 1 equals negative 3 times 1, which is negative 3. And u of 0 is negative 3 times 0, which is 0. So the integral that we're doing in terms of u is from 0 to negative 3. From 0 to negative 3. Okay. So now I can take the antiderivative of e to the u, which is just e to the u. So I have negative 1/3 of e to the u evaluated from 0 to negative 3. So that's negative 1/3 times e to the negative 3 minus negative 1/3 times e to the 0. So this would be negative 1 over 3e to the 3. Minus minus makes a plus. So plus 1/3 times 1. And there's a few different ways we could write this answer. We could say, I could have left the negative 1, or the negative the negative exponent free. I could have left that on the top and called this negative 1/3, e to the negative 3 plus 1/3. I could have done that. I could say that this is negative 1, 3 over e to the 3rd plus 1/3, and I could leave it like that. Or I could get a common denominator and say negative 1 plus e to the 3rd over 3e to the 3rd. So that would be like I took this one and multiplied by e to the 3rd over e to the 3rd to get that common denominator. All of these answers are right. So in a free response question, all three of those would have been fine. In a multiple choice problem, you'd have to recognize which one was the one that you had, if the one you had matched those.